Hello, Algebra 2 students. You're going to notice at the top of today's notes, it says days 3 and 4, because this takes us kind of 2 days to get through. So you're going to watch 2 different videos. One that you're responsible for, obviously, today, and then you'll work on that homework tomorrow, and then a second one for tomorrow, all right? And it's all about modeling linear functions. So you definitely need your calculators. So make sure that that is nearby, all right? It's more for the day 4 piece of it, but we should get to some of that in today's notes. So first things first, it says, recall when a real world situation involves a constant rate of change, that's when a linear function is appropriate, all right, to model what's going on. So we've done modeling with absolute values. We've done some with parabolic, so like parabolas, quadratics. So today we're focusing on linear. So the first one says, write a function that models the given situations, determine a domain from the situation, and then graph the function using that domain. So let's draw a little sketch and then identify the range. All right. So this first one says that Joyce jogs at a rate of 1 mile every 10 minutes. So Joyce would be my girl. It's about my pace for a total of 40 minutes. Determine a linear function that models her distance in miles as a function of time in minutes. Right? So I know often I will tell you guys to figure out like what are the x, what are the y. So here we're using d and t, but same idea. So since we're going to sketch it, I want you to think about which is the x, which is the y. So the time, almost always, that's your independent variable or your x value. And then your y value in this case is the distance. All right, so we've got distance in miles. Over here, we've got time in minutes. So those are both important to note here, right? And then it's saying that for every 1 mile, it takes her 10 minutes, right? So down here, we got 0. We would say after like, all right, 10 minutes, then she's gone 1 mile. And then after 20 minutes, she's gone 2 miles. So her pace makes it really easy to kind of figure out what's going on for a total of 40 minutes. So we can go all the way out to the 40-minute mark, which would make sense that she would have gone 3 and then 4 miles right there. So when it says draw it, it's only over that specific domain. So we can start at 0 and then sketch that you would just have that one little line segment here, right? Then it's saying model the function as an equation, right? Well, since it's linear, we know we should be able to write it in, y equals mx plus b form. In this case, though, the x and the y would just be the t and the d, but we'll get to that in a second, all right? So what you have to think of is what is the appropriate slope of this line, all right? So when you think of the slope, we're talking about the rate at which this lady is running here, right? It's always change in y over change in x, or in this case, it would be the change in distance over the change in time, all right? So when we think about it in that regard, for every 1 mile, it's taken her 10 minutes. So your rate would be 1/10 here. Right? So that would go in for our slope. And then as for where she's starting at, well, starting at 0 in this case. So we can put just a 0 here. And there's our equation. Now let me turn it into distance and time. This would be distance is 1/10. Oops. However much time has gone by. All right. And you might know the equation like distance equals rate times time. And so that kind of rings true for what you're looking at here, that distance equals the rate times the time. All right. And that's it. That's your first little equation. All right, now it's saying suppose that Joyce jogs only 30 minutes, so she doesn't have as much time. How does the domain change? How does the graph change? How does the range change? Oh, it just occurred to me. We were supposed to talk about the domain and identify the range. So here, before we go into changing anything, for that given domain, so the domain was from t going from 0 to 40, the range then went from 0 up to 4. So if she's got 40 minutes, she's got 4 miles that she can cover, all right? So if she only has 30 minutes, then the domain in this case, would go from 0 to 30, all that's going to happen to the graph, it's still going to have the same slope. It's just going to be a smaller segment. Right. So you could think of it as, a little bit of like a shrink or something along those lines. How does the range change? Well, she can't run as far then. So the distance that she can cover would then only be up to 3 miles, right? So this is your X, that's your Y. All right. Second question. So think about what we did. We sketched a graph, then we calculated the slope based on the graph that we were looking at, then wrote the equation. I sort of want to follow that same format for this next one. So it's saying a candle 6 inches high burns at a rate of 1 inch every 2 hours for a total of 5 hours. Right? So when we look at this, we're talking about the height, since it's 6 inches high, and then the amount of time. So when you sketch it over here, time is our independent variable, right? So it's always our X, but we can call it T in this case. And then our Y, that's going to be the height of the candle. And we can call that H, all right? So it's 6 inches, and it burns at a rate of 1 inch every 2 hours, all right? So you're actually given the rate here. So the rate, it's burning down 1 inch every 2 hours. Think that's Y over X. So that's a perfect setup right there. All right. So if it starts at 6 inches, so like, let's just call that 6 up here. You could grab graph paper if you want to be more specific, but this is good enough otherwise. And then it's burning at a rate of every 1 inch every 2 hours. So it's getting shorter. So it's going down 1 for every 2 hours of time that goes by. So if 2 hours, it should drop down to then 5 inches. And then if another 2 hours goes by, it's going to drop down another inch down to 4 inches and so on. All right. And now it's saying it's only burning for a total of 5 hours, because after a while, maybe you got to leave the room. You don't want to leave a candle burning. That's dangerous. So you can kind of sketch this in. If you happen to have a straight edge near you, you could use that. I've got one sitting here, so I'll do my best. And I draw it in like this. Oops, except for I have to extend it to 5. So let's say like here-ish, all right? So a couple of things. We want to establish the domain and the range, but they said let's use interval notation this time. Right? So our domain is going from 0 to 5. All right, as for the range, you can use the graph or we can use the equation, but we know that the range is going to go bottom to top. So if we don't know how low that candle height goes just yet, we could hold off on that. It's going to max out though at 6. The candle's not magically getting smaller. So let's create an equation so that we can finish that piece of it. So when we think about this, this is definitely linear again. So we've got y equals mx plus b. All right, well, in this case, we can go the height, the slope. Now I said it's going to drop at 1 inch every 2 hours, but when I wrote it, I just wrote it as 1 over 2. If it's losing that height, it really should be minus 1 over 2. So negative 1/2 is what would make sense here, times every hour. And then you also have to consider, where is it starting? Oh, there's Teddy. So back here, it started at 0. So we were plugging in a 0. Here, it's starting at a height of 6, right? So that's your y-intercept there. So then plus 6. So that's the equation. So now when you come back to answer the range, if you can't tell from the graph or if you're not 100% certain, you can actually plug in, right? So what would we be plugging in? Well, we want to know what's the corresponding height when x or the t value is equal to 5. So I can kind of off to the side here say, all right, what's the height when we plug in 5 here? And then calculate it from there. So negative 1/2 of 5, so that's 2.5. And then add that to 6. So 6 minus 2.5, that's going to drop you down to 3.5. So that would be the range of values. So domain left to right, range bottom to top. Okay. So we've got our equation here, our domain and range there. So keep in mind, if it's decreasing, then the slope is negative. And so you kind of have to look at it case by case. Could I pop that into the calculator to double check that that makes sense? Absolutely, right? Okay, on to the next page. This next concept might remind you of something from way back in Algebra 1, right? This here, when it's saying when given a set of paired data, so like X's and Y's, those pairs, saying you can use a scatter plot to see whether the data shows a linear trend. So like, do you see a line emerging from it? If so, you can use your graphing calculator to perform a linear regression and obtain a linear function that models the data. So the calculator will create the equation for you versus like what we just did where we created it ourselves. It's saying you should treat the least and greatest X values of the data as the boundaries of the domain of the linear model. And the reason for that is when you think back to what we had here, these can't go on forever. I mean, I don't know Joyce, but I imagine at some point the girl gets tired, she can't keep running. Same thing here. The height only makes sense until it drops to 0. And then at that point, the candle's burned out. It wouldn't make sense to go beyond that, all right? So it naturally has a domain that kind of is set for it. So the second part says when you perform a linear regression, your graphing calculator is going to report the value of the correlation coefficient R, all right? To make sure that you get the correlation coefficient R, you have to make sure the diagnostics are on in your calculator. I'm going to show you right now, and I want you to have your calculator with you so that you can do this. But if for some reason it doesn't work or if you're not sure, make sure to ask me in class, all right? So to turn the diagnostics on, if you have one of the newer calculators, it's under mode. So I'm going to show you on my calculator, make sure I can see what's going on here. Your mode is right next to the second button there. So if you hit mode and then you arrow down, you can see on mine where it says stat diagnostics. I'm going to zoom in a bit here, right? And mine are off. I want to turn them to on. So I can hit on by just hitting enter so that it's now highlighted, and my diagnostics are now on. Now, if you have a slightly older calculator, so like the chunkier looking graphing calculators, you might not see this under mode. In that case, how you would do this, let me zoom back out a little bit, is you would go to second 0, which if you look above the 0 button, you're going to see the word catalog. So the catalog is actually good to know about just because every single function on the calculator, so right here above 0, you're going to see that word catalog. So if I hit second 0, every single function in alphabetical order is on there. So like the first one, there's the absolute value. So if you ever can't remember where something is, you can go into the catalog. You just have to be able to find it alphabetically. And you're going to go down until you see diagnostics on. When you see diagnostics on, you'd hit enter, and then you hit enter again until it says done, okay? Now you're going to know if that actually turned on when we do our regressions, because then you'll see that correlation coefficient, that R value pop up, all right? So try it right now, turning the diagnostics on, and then we'll talk about it in class as well, all right? So something to keep in mind is that correlation coefficient, it's going to tell you about the graph that you end up with. So the variable can have a value anywhere from -1 to 1, right? And what the correlation coefficient measures is the strength of the relationship between your X and Y variables, all right? So you have an example of 6 different like scatter plots here of what you could end up seeing. If your relationship is linear, it should look something like either A and D, where it's a really strong correlation, or B and E, where you can still kind of see the pattern, all right, but it's just not quite as perfect. Right? So what would the R values look like for those ones? Well, if it's a perfect fit, R is going to come out as +1. It can also come out as -1 if it's a perfect fit, the only difference being that the R value also reflects what's going on with the slope. So if it's a positive slope, it would be positive. If it's a negative slope, it'll come out negative, all right? So something to keep in mind, the R value, the positive or negative matches the slope. So these first two, these are examples of basically like a perfect fit. All right, here we would still call this a strong correlation. You can tell that the data is trending up to the right or trending down to the right. So this is considered a strong correlation where you can still see like, hey, cool, this is what's going on. In that case, a strong correlation, the R value here would come out between 0.5 and 1. Or if it's negative, it would come out between -1 and -0.5. Right? When you get down to cases like these last two, if the points are all over the place and there's really no trend at all, this is what we would consider as either weak correlations or maybe even no correlation. What R values would you expect in that case? Well, R value is near 0. So anywhere between -0.5 and +0.5. So example, if R value comes out as 0.2, what they're really saying is there's no correlation going on here that they can detect. Or maybe you get a case like this one where there's definitely a relationship, but it's just not a linear relationship. So this would be a nice quadratic relationship in that case. So when it says you can use the linear model to make predictions and decisions based on the data, making a prediction within the domain is called interpolation. Making predictions outside the domain is called extrapolation. All right. I'm thinking let's go one more and then we will stop there. So this very first one here, I'm going to slide up, is saying a photographer hiked through the Grand Canyon. Each day she stores the photos on a memory card of her digital camera. When she returned from the trip, she deleted some photos from each memory card, saving only the best ones. All right, the table shows the number of photos that she kept from all of those stored in each. So if you take a look, like this day she took 117 photos and then she only kept 25. And then took 128, only kept 31, and so on. All right. It says use the graphing calculator to create a scatter plot of the data, find a linear regression model, and then graph the model. Then use the model to predict the number of photos that the photographer is going to keep if she takes 150 photos. All right. So what I want to do is just kind of walk you through what's happening here. So the first thing, to create a scatter plot, we are going to have to enter this data into our lists. So the number of photos taken, that's going to be our X value. How many she ended up keeping, that's going to be the Y value. So we're going to put this data into list 1, this data into list 2. Now on your calculator, right, now there's a little reference sheet. I think I attached it to the back of your notes packet that you guys can rip off if you would like. It'll run you through all these steps, but to find it, you're going to go to Stat and then Edit. And then what you're going to see are a bunch of lists. Most likely there's nothing in those lists. If there is, you can clear them out. Otherwise, you're going to type into list 1 the X values and then into list 2 the Y values. So just as a reminder, that was Stat and then Edit, and then you should be in your lists. So into L1, we're going to type in order 117 and then 128, 140, 157, 110, 188, and then 170. All right, into list 2, you're typing in 25, 31, 39, and so on. So take a minute, type these in. Now, because you will type in so many numbers, it's worth it to take a second and double check and make sure that you did not enter anything in incorrectly. So take a moment and look, make sure you're looking good. Right? And then to create the scatter plot, what we're going to go to is we're going to go to second and then Y equals, and you're going to turn on your stat plot. So right here, second, and then Y equals, and turn on your scatter plot. So where it says stat plot, mine says off right now. You're going to hit that and you're going to change it to on. And now if you look at the choices, I'm going to zoom in a little bit so you guys can see better. You're going to turn it to on. The first one is a scatter plot. There's a histogram. There's a box and whisker. We're not going to use those guys. Just the very first one. Your X's are your L1. Your Y's are your L2. If you want, you can change the marking. You don't need to. And you can change the color if you're feeling fancy. Otherwise, all you're going to do is you're going to graph this all right, by going to Zoom Stat. So once you have the data in the lists, to graph this, we're going to go to Zoom Stat, because what that's going to do is it's going to give you the window that fits the data the best. So Zoom Stat is Zoom 9. And what you should end up with is this. Now what you're going to notice is what's on my calculator matches exactly this over here. Here's a little screenshot of what it should look like. All right, so this first one you can kind of watch and just model through it, right? So when it says let X represents the number of photos you took, Y represents the photos she kept, use a viewing window that shows X values from 100 to 200, Y values from 0 to 60. So when you choose Zoom Stat, it kind of picks a nice window for you. But if I go look at the window, see how it goes from 102 to like 196? That's basically 100 to 200. And then mine specifically is showing me from 15 to 57 is what my calculator picked. So it's not quite 0 to 60, but you get the idea. It's still in that same basic range, right? When it says, what do you notice, right? Well, I'm asking you, do you see a little bit of a trend? What I'm noticing is that it kind of looks like the line that's got a slow little slope up to the right. And so the more pictures she took, because that's your X value, this is your photos taken, right? Then this is the pictures kept over here. It looks like the more pictures she kept. Which totally makes sense in this scenario. The chances that you'd take more pictures and then not like any of them is not super likely. All right. The last thing that I'm going to do on this video with you, and then we're going to take a little break here, is onto this next page. It's saying perform the linear regression. All right, to do the linear regression, you're going to go to Stat and then over to Calculate. And then choice 4 is linear regression. And it looks like linreg. All right, so I'm going to go Stat and then over to Calculate, and then choice 4 is linreg. You see AX plus B, right? And maybe I'll even write that the way it looks, AX plus B. All right, when you hit enter, it's going to ask you, is the X list your L1s? Y list is L2s. Those should already be in there. You don't want anything under the frequency. Don't worry about storing it. Just go down to Calculate and then hit enter. And then what it does for you is it kicks out the answer. And what you should have gotten kicked out here, it matches what's going on over here. So the equation to the nearest hundredth, the A value is 0.3309, so we'd say 0.33x. The B value was negative 11.33, so we're going to plug that in right here for the B value. So minus 11.33. And now, if your diagnostics are on, you should also see the R values. So it should have came out as 0.848 and keeps going. If your calculator did not produce an R value, that means you did not successfully turn your diagnostics on. So make sure to ask for help the next time I see you. Otherwise, the last thing I want to take note of is if that correlation coefficient is 0.848. Think about what that means. When I come back here, 0.848, that's between half and 1, that's a strong correlation right there. So we would consider this to be a strong correlation, all right? So then when it says predict the number of photos, let's save this for class.